In this video, I want to show you a simple example of what safety means in Rust. Obviously, in a short video, we're not going to see anything too complicated. The purpose here is just to motivate you to take a deeper dive into Rust. Here's an example from the Rust book. Let's go through it line by line. Line 1 starts the main function, which is run by the executable. Line 2 defines a new variable named v to be a vector with the numbers 1 through 5. In Rust, usually all memory is owned by a single variable. So in this case, v owns the vector. Line 4 defines the variable first to be a reference or a pointer to the first value of the vector. It's a reference, so it doesn't own the memory, but it does refer to it. Line 6 pushes an extra value onto the end of the vector. Finally, line 8 prints the value of the first variable. We hold a reference to the first element while adding a sixth element. Is that a problem? Let's turn on the Rust analyzer and see what the compiler would tell us. On line 2, we see that the type of v is a vector of integers. On line 4, the type of first is a reference to an integer. And on line 6, we have an error. Cannot borrow v as mutable because it is also borrowed as immutable. We can hover over the error and click to see the actual compiler error. The compiler annotates our code and explains that line 4 does an immutable borrow of v, line 6 a mutable borrow of the same v, and then line 8 uses first, which uses v. Therefore, line 8 has a use of the immutable borrow of v even after it was also mutated. I understand that technically speaking, first references the vector and v mutates the vector when we push 6 on. But what could possibly be wrong with this? I'm adding to the end, which won't change what's at the beginning. The compiler has to guarantee safety. So it sometimes has to forbid behavior in corner cases that as a human we can prove are actually safe. Is this one of those cases? Before I give the answer, feel free to pause the video and reason about it and decide for yourself. Is this code safe and the compiler just couldn't prove it? Or is this code unsafe and the compiler is saving us? To answer our question, let's imagine what's going on in memory. The vector is actually a pointer to the contiguous data on the heap, as well as the capacity and length of that data. And first just points to a single element on the heap. So when we push 6 onto that vector, if the capacity was greater than the length, then everything would be safe. But if the vector was already at its capacity, like in our diagram, then to keep the elements all contiguous, we need to allocate new memory on the heap and copy over all of the item values. Then we switch our pointer to point to the new memory, update the capacity to be a larger number, and clean up the old memory on the heap. Remember that v owns the memory, so it's fully safe to clean it up, and we don't need to rely on a garbage collector. This way, we are safe and fast. Safe? Someone's probably screaming that first points to nothing, so it's not safe. That person is correct for C or C++, but for Rust, it's still safe. The compiler guarantees us it'll never generate code that could possibly do anything unsafe. So it doesn't matter that a pointer points to nowhere, since the compiler guarantees that no instruction will ever follow that pointer while it's still pointing to nowhere. Now that the vector has more capacity than length, we can push 6 onto the back. So far, so good. But how about when we then try to print first? Yeah, that's the problem. So in this case, the compiler was correct, and the code was not safe. There are many fixes. We could make first a copy of a value rather than a reference to that value, or we could clone the vector. Instead, let's just move up the print line. Even before I saved the file, the error went away. Now the Rust analyzer sees that first is never used again after the mutation of v, and therefore it's okay even if there's a dangling pointer. With no problems, I can then run the program and get the expected output of 1. While this simple example dealt with memory safety, Rust does similar things for thread safety. with the compiler proving that memory won't be modified or cleaned up on one thread while being used on another. This makes it harder for code to compile, but quicker to write code while I can count on the compiler to notice race conditions for me. The Rust community calls that fearless concurrency. Here's a small example using a module, or crate, named Rayon, which gives us high-level parallelism primitives. The example is almost straight out of the crate's documentation. It also uses the standard library thread channels for simplicity. We send numbers to different threads to in parallel square them and then send them back. The example is trivial. What's amazing is that the Rust compiler is making sure that every thread owns all the memory it needs so that we can focus on the higher level concerns while being guaranteed minimal levels of memory and thread safety by the compiler. If you're now interested enough and want to learn more about Rust, then in the next video I can recommend some setup and point you to some resources to learn more.